Today's experiment is about synthesis of acetylic salicylic acid type of drug, and we shall see how we can synthesize this drug. So acetylic salicylic acid, also commercially known as aspirin, is a drug that belongs to a class of drugs called analgesics. These drugs are simply known for their action to relieve pain, and that's why the analgesic simply means painkillers or pain relievers. But also, these drugs are administered not only for pain but also for fever, inflammation, or blood coagulation. And they're also called blood thinners, not because they thin the blood, but they clarify the blood vessels so that blood can flow smoothly and easily. So in these classes we have, for example, in here we have about four kind of analgesics, four types of analgesics, beginning from aspirin, acetaminophen, ibuprofen, and naproxen. And if you look at the structures, all of them are organic compounds. That's why, in fact, we are trying to synthesize them here in our practical organic chemistry. And because they have different functional groups as well as some common functional groups in between them, you can see they have common medical actions as well as distinct medical actions between them. Anyway, in this experiment we will be looking at least at the synthesis of one of these drugs, and we will take the aspirin as a focus of our study. So aspirin is synthesized using substitution reaction, and the general reaction is as you see in the slide, where salicylic acid reacts with acetic anhydride with phosphoric acid as a catalyst to give us acetylic salicylic acid, that is aspirin, and acetic acid as a byproduct. So the mechanism goes as follows. So the first part, and the first step is where phosphoric acid protonates one of the carbonyl groups of the acid anhydride, making it more electronegative. So when this protonated oxygen takes back the pair of electrons towards itself, it creates a carbocation on the carbonyl carbon, and then the OH, the hydroxy part of the salicylic acid, comes and attacks this carbocation. This is where we see the application of substitution reaction in this drug synthesis. And then because the OH hits a pair of electron, we will see a plus charge in the oxygen, and we have to neutralize that by removing a hydrogen, which will give us an intermediate product. And from this intermediate product, which you're looking at the left side, at the top left side of the slide, you can add a second proton into the carbonyl carbon, and then again the oxygen will be protonated and become more electronegative, and then you can proceed with electron delocalization. When you push the electrons of the oxygen hydrogen in the first carbonyl carbon attacked by the hydroxyl group of the salicylic acid, then the carbon oxygen double bond between this carbonyl carbon and that of the middle oxygen in the acid anhydride will be split to the acyl fragments, and because of this delocalization, one of the carbonyl oxygens has to open and neutralize the charge on that oxygen and comes out as acetic acid, and the left one as acetylic salicylic acid. So without the acetyl group, the structure is called salicylic acid. When we add the acetyl group, we call it acetylic salicylic acid. So synthesis of this compound is very easy. You just need to have a clean, dry Erlenmeyer flask of small size, about 550 milliliter, and you have to add 1.4 grams of salicylic acid followed by 3.3 milliliter of acetic anhydride. So and then you can add 5 drops of 85% phosphoric acid. When you add the powders of salicylic acid, if you in case left some part of the powder in the walls of the Erlenmeyer flask, you can make the addition of your acetic anhydride through that path by inclining the flask to about 30 degrees, so that you can wash them out. You can wash the powders out into the bottom. And then once you add all these ingredients, you can heat the mixture in a hot plate to about 85 to 95 degrees Celsius. Preferably, you can also use hot water bath. In either way, you have to heat the mixture for 5 minutes. But because water bath is safe, so that the temperature do not exceed the 95, you can also alternatively use water bath for the heating. After that, you can remove the flask and immediately add 2 milliliters of water into it. We do this to make sure that any excess of the acid anhydride are decomposed, and you need to make sure that you're adding this water at the final temperature of the reaction mixture. In fact, if you're using the hot plate, the temperature could be a little bit above that, and you need to cool down a little bit so that it comes between 85 to 90 degrees Celsius, and then you can make your acetic anhydride, your water addition. The next, you can add 20 milliliters of water again, and let the flask stand for some time, so that you allow the formation of crystals. And crystals sometimes do not form if especially when you do not follow the experimental procedure strictly. You can have hard time in recovering crystals. So in that case, you can scratch the inside wall of the flask right at the top of the surface of the solution using a stirring rod, preferably stirring rod. And then once you see your crystals start to form, you can place your flask in ice bath, and then you can add cold water, about 10 to 15 minutes cold water into the flask, so that it will it will help uh, it will help uh, formation of crystals. In fact, you should make sure that the water is very cold, otherwise it will disturb formation of crystals rather than assist the formation of crystals. You should also cool same amount of water for the next experiment, because after you cool down the crystals in ice baths, you will need then to recover your samples through cold filtration by placing your samples in a filter paper inside the bottle or funnel, and you can turn on the vacuum pump, and then the vacuum pump will do its job by sucking air. In that way it will filter out the samples and make them dry in a cold environment. And then you can use your previously cold water in a beaker to wash your samples, and you can do this while the vacuum filtration is running. You can add using a pipette, okay, plastic pipette or glass pipette, and you can make round around the samples, and in that way you can effectively wash your samples. Then finally you go for analysis, taking your sample. However, before you make any analysis, make sure that your samples are very dry. Normally we leave the sample overnight, but I don't think you should do that in here. Rather, you can, if you effectively wash the sample and place it in a very dry place, you may also need to change the filter paper or add another filter paper at the bottom of it, so that it will aid the drying. Or you can also put over a silica powder. If you have a silica powder in the laboratory, you can put the sample over a silica powder, then it will dry very fast. So with the dry samples you can weigh, so that you can determine the percentage yield. You can calculate your theoretical yield from the reaction I gave you in the third slide, whereas you can take the actual yield from measuring your experimental yield. By that you can calculate the percentage yield. For solid samples, for solid sample products, it's always advisable to conduct melting point, because it will tell you if you got your pure sample or not. In that case, you may need to do the experiment again, or you may need to recrystallize, for that matter, if you have if you have impurities in the sample. For information, the melting point of acetylic salicylic acid is between 140 to 142. If you have an access, also it's better to measure the IR and NMR, so that you can easily compare the spectrums with the standards, so that you can confidentially tell that you have synthesized the acetylic salicylic acid. And most importantly, safety. This is chemistry. You must always be open-minded and alert in every chemistry experiment, because there is no safe, there is no safe chemical, okay? you have to remember this always. There is no safe chemical in the laboratory. Even water itself, you don't know, it can be contaminated, and you cannot guarantee that you can drink water and claim that it is pure. Anyway, you do remember that we have used phosphoric acid and acetic anhydride in this lab. Especially the acetic anhydride is known to cause respiratory disorder. Even it can result in permanent eye injury if the vapors itself comes in contact with your eyes or you breathe them. So that's why we advise you to do the experiment entirely in a fume hood. Even if you have to transfer liquids for the transfer liquids or add water, and you have to do these activities during the lab, try to do it inside the fume hood, but also remember to put your goggles. They are there to help you in such times. So you get to take care in handling these experiments, as well as in handling all the solutions or mixtures. And it's easily forgotten, but when you handle any chemical bottle or any chemical containing beakers, try to make the beaker away from your face so that you cannot accidentally inhale any vapors of the chemicals. Yeah, I do know that the phosphoric acid and acetic anhydrides are not that much acidic. However, because in this experiment we involve heating for our reactions, then there is high probability that these chemicals can undergo violent reaction, can be violent, so they can be more reactive, and we have to be careful for that reason. Well, that's all I have for this experiment. Again, if you have any question, not only on the experimental lectures but also on all these quizzes that are coming from these lab lectures, you can email me, you can write a comment on the YouTube, or you can reach me out by by writing email, of course, and I'll be responding to you. And thank you for your time.